Hello. In this video, we're going to talk about the STL containers again, but this time we're going to talk about what's known as an iterator. So as we saw last time, the containers have different properties uh, based on how they're, defined under the hood. So a vector is actually an array underneath. The difference with array in the class array and the class vector is the vector can grow. The reason of having a class array again is that it will keep its track of the size for you. Otherwise, it's really honestly just an array. A vector is using an array, but it has the ability to grow when you add enough stuff to it. So it'll double in size. Deck, double-ended queue, is very common. In fact, most people don't talk about it really, but it is really common data structure because it supports efficient insert at front and at the backside, and deleting from the front and the backside. And this is common, for example, when you have what's called a pub sub, publishers publish and subscribe architecture, where you have some code like in a separate thread or something that is adding stuff to the end of the deck or end of the container, and another function that is taking stuff off the front. So you can imagine something is like crawling the web and putting everything it finds on this queue, and something else is taking things off the queue as they appear in order to process them and put them in the database or something. So in that case, you want to efficiently put stuff on the end and take stuff off the front. So that would be a good use of a deck. A vector would not be efficient for that, because if you take stuff off the front of the vector, it has to move everything down. A linked list, I suppose, would support this as well, as long as you kept pointers to both sides of the list. But I think deck is most commonly used in that kind of scenario. Then a list, there's a forward list and a regular list. The regular list is bidirectional. So regular list supports putting stuff at the front and the back efficiently. But of course, the difference with the vector and the deck versus a list is vector and deck allow efficient discovery or access to elements in the middle. That would be called random access. In other words, access anything you want at any time, any position. It should be efficient. And efficient, we always mean efficient as almost always constant time. Like it's not any slower just because you have more stuff in your vector. Sometimes we mean efficient like linear. It takes only 1,000 steps if you have 1,000 things. But in this kind of situation, we're usually talking efficient means constant. So it's not efficient to jump to the middle of a list, because you have to, if you're not already there, if you're at the front, that's where your pointer is. You have to move all the way to the middle. And we also have set and unordered set. There's slight differences in their efficiency for certain operations, but set keeps things in order and unordered set doesn't necessarily do that. But their main thing is they don't allow repeats. So there's no left or right concept. You don't put stuff at the front or the back. You just put stuff in the set. And then a map is a key value pair, a collection of key value pairs. It's kind of like a set of key value pairs, because if you have the same key, then it will replace the value. So here, obviously, there's no idea of a first and a last, not really position-wise. So you don't really put stuff at the front or the end. You put stuff in with a key and you take stuff out with a key. And it's designed so that when you give it a key, it'll efficiently find that position. And so that would be constant time also. Now, they do have a lot of differences. Some have a real concept of a left and a right and putting stuff on the front and the back. Some don't. Some avoid repeats. Some don't really have particular order at all. But for algorithms like finding something, is this thing in your deck? Is this thing in your map? Is this key in your map? Is this value in your set? It'd be nice to have a generic way to do that. And sometimes you even want to sort your collection. Now, you're not going to sort a set. It's already sorted for one thing. You're not going to sort a map either. But a vector or a deck or a list, you might want to sort that. And there's other operations that we won't get into, but there are some things that you want to do and not have to care about what kind of container it is. But these containers are so different, they don't even have a real idea of position. So how do you go through all the elements? Like if you're trying to find something, how do you go through all the elements in these very different kinds of containers? So what they've come up with is an idea of an iterator. Iterators are this generic way of going through the things. Depending on what you're going through, it may not go in a particular order, but it will go through all of the things. There's many types of iterators. There's, you might say, regular iterators that go left to right, so to speak. Then there's constant iterators, which means you can go through the thing, but you're not allowed to change anything when you go through it. And then there's the reverse iterators that go right to left, if that makes sense. So in a case like a map where it doesn't really make sense what right to left even means, it's okay. It's still defined. It'll just do whatever. It goes through the elements. But for a vector, it'll really be right to left and so on. So iterators are the generic way to go through collections in the STL library, or containers in the STL library. And what's interesting about an iterator is it's treated like a variable, but it really is a class. It's an object. So it's not like it's a number, like a position. So if you've imported one of your containers like list or whatever, you can make an iterator. Let's go through the vector with the iterator. The way you establish an iterator is its formal type is, it's actually defined as a subclass inside vector or inside list or whatever it is. So you would use the double colon iterator. You can do reverse iterator, you can do constant iterator, but most common is just a regular iterator. We often call it IT, but I'm going to have a couple of them, so I'll rename it. So there is my type of thing. Now, you always got to match the type of values in your container, in this case int. Otherwise, it won't even know what it's pointing to. Now, you have to make it equal to something, and you saw here iterators have begin and end, and that's it. You can't jump to the middle with an iterator because not all these containers support that. That would be the at operator or at function or the brackets operator. So since they don't all support that, there's no concept of that position. You only can do the begin. So you always start with the begin. And what you're going to do is take your vector object, whichever vector you're going to iterate through, and say begin. Now, when you have your iterator established, assuming you got something in your vector, you can then treat it like a pointer because they did an operator overload for star, like we've done also. And it will then extract the value from the vector, which should be the first value. Oh, I meant vec it. So it's the 5 because that's the only thing in there, frankly. And it's at the begin position. Now, I'm not sure this has even been defined, but we're going to do a plus plus on the iterator to move it forward. Oh, I meant vec again. Okay, it is defined, but what you're going to more commonly see is the plus plus before because it doesn't require that the iterator is copied. So you're mostly going to do vec plus plus like that. And then let's grab the value then. So we moved it forward one position. It compiles just fine, but it says 0. We actually sort of got lucky there because there's nothing at that position. We only have one thing. If we do it again, who knows what it's going to do? It might crash or whatever. Yeah. So it's just zeros, but if we do valgrind, I bet it will tell us it's no good. Yeah, all these invalid things. So if we take that out, let's see what valgrind says. Yeah, no problems. So that's one of those cases where, okay, didn't crash. Probably should have crashed. Turns out we didn't actually access memory outside of our program's space, but if we'd done this enough times, we would have started accessing memory that doesn't belong to our program. And then the operating system would say, hold on, I'm going to throw you out because the operating system comes in at that point. If your program is just accessing its own memory, even though it's not really valid data, what you're really doing is just walking into your other containers accidentally. So you still don't want to do that, and Valgrind will notice that. So this plus plus really can't be done if you only have one thing. What you can do to notice that is check that vec it equals what's known as end. So this should say 1 because it should be a true statement. First it should say 0, then it should print the 5, then it should say indeed it is true because we did a plus plus. Yep, so no, it's not at the end. There's the 5. Yes, it is at the end. So what that means is end is defined for every iterator, or every container. It returns an iterator, and you can compare your existing iterator to that end iterator. And if it's the same, it means you've gone too far. So end is always too far. End is never actually a position of anything. It is always too far past, like you've run out of things. There's nothing left. Your iterator is bad. And there are some I don't know if this one's defined this way. I wonder if we can do a minus minus. I know some can't, but let's see if this works. There's some called forward iterators that do not have minus minus defined. So vectors can go backwards, but I suspect if we had a forward list, it would not have a minus minus defined for its iterator. That's probably the reverse iterator issue, which this one doesn't have. See, there's no R begin and R end. So if you were to do R begin and R end, it would just start on the right side. And you'd probably do minus minus. So there's an iterator for a vector. What you're normally going to do is use a loop. So here's what the loop would look like. You'd say for, and then that whole thing to set it up, as long as it's not the end, and then go forward. So this is like your new complicated way of printing the contents of something. But it would work for a set, it would work for a list, it would work for a deck. So again, we have, just like you say for int I equals 0, now it's for iterator equal begin. And notice it's the beginning of the vector, whichever vector you're trying to go through. And as long as you haven't gone too far, increase its position. It prints all the things, which is just one thing. Now, what that means when I say it's general is you could say set int my set. And now you can walk through your set when there really was no other way to do this. There are no functions defined for sets such that you can walk through it, except something like this. Now, normally you're going to just call it IT, by the way, unless you have a reason to use a bunch of different names like this. So there's that 1, 5 in the set, but if I add 51, there's the 51, and if I add 10, since sets are ordered, I expect it to be ordered. 5, 10, 51, yeah. Okay, so that's how you can walk through a set, just the same as you walk through a vector. Now for a map, it's kind of interesting. Do map, and then we had string int, and map, my map begin. Okay, so it's all correct now. This should go through all the elements of the map, but recall that what's in a map are pairs, actually, key value pairs. So that's why it's mentioning pair everywhere here. Pair is a class, and what you can do with a pair is get the first and second. I wonder if this is going to work, actually. First would be the key, and second would be the value. No, it doesn't like that. Let's try this. There's your keys, goodbye and hello. They actually are sorted. These are my keys. And if you wanted the other thing, you would say the other, which would be value, get the pair again, and then it'd be called second. It's not really a key and value because it's using a pair, and pairs are more generic than maps, so they call it first and second. So you're effectively printing the contents of the map. It happens to be sorted by the keys. Now, this star syntax, they've actually done an overload for the operator arrow to behave the same way. So they really want it to look like a pointer, basically, these iterators. So you can do these arrows as well. So it's the same thing. Yeah, printed each twice. All right, so that's how you walk through things. Almost always you're going to do it like this. You maybe would find a scenario where you want to do a R begin, R end, and minus minus if you want to go right to left. Now with that, if we import algorithm, you get access to some neat functions that you wouldn't want to define yourself. So let's go to the algorithm header, and that's algorithms library. And you get things like you can run a function, kind of like you give a function pointer effectively to see if that function is true for all the elements. You can count the elements that match a certain function. More often you're going to use find. So let's look at how find works. And again, there's 50 different ways to use it, but really we're going to use this one. So what's being stated here is you call find, give it an iterator to the start and an iterator to the end, and what's the thing you're looking for. And it will give you back an iterator. So if we want to look for if the number 51 is in my set, then I'll say set int iterator result equals find. Now I want to tell it really the whole set. Look in the whole thing. So I would say from the begin to the end. You're almost always going to say begin and end for a find, unless you got some reason to only look in half the container. And I'm looking for a 51. Now, result is going to give me the position, or it's going to give me an iterator to the position. So I can, print it, for example, and it should be the 51. So it prints 51. If I look for 52, it's time I got to run it with Valgrind. Oh, it just prints nothing, I guess. So that's interesting. Or no, it printed a 3. Interesting. I think it went off and looked at that 3. I suspect. What's really happened here, you don't want to really do this. You want to say if the result is equal to the end, it did not find it. So I was looking for 52, it should not find it. Not found, it says. If I look for a 51, I should say found. All right, so when you use something like find, you give it iterator, and the thing to find. So notice this function should work for anything that supports iterators, because if it can have the starting position and it knows when to stop, it could just go left to right, or it just say plus 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 until it finds it. If it never finds it, it would give you end, because that's really the only way to tell you not found, it's bogus. Here is a bogus, like a bad iterator. Whereas if it is found, it'll stop when it does find it, and it'll give you the iterator to the position. And when you got that position, you can do things like insert or go to the next element or whatever. But mostly what you're going to do with find is you're just going to say yes or no, it was found. And then there's some other things like sorting, where likewise you give it a start and end, and it will then sort your thing, sort your container. So you can say something like sort myvec.begin and myvec.end, and it will then be sorted. Now notice it says random iterator, not just input iterator. There's, like I said, actually a whole hierarchy of iterators, all these different types. Vector, Deck, some others support random iterators because they allow random access. When you do a sort, it's efficient to jump around and copy things all over the place, so you want random access. A list does not have a random iterator kind of iterator. It has just a forward iterator or a reverse iterator, but not a random one. So lists have their own sort function. You can sort a linked list, but you want to do it with code that is designed for sorting a linked list. So the list class itself has its own sort method. So that's what you got to use for a list. All right, so all different kinds of functions here. Find the min of the collection, find the max of the collection, and so forth. They probably take interesting. I expected them to take iterators, but I wonder if that's this version. I don't know. I don't see the version with iterators, so that's sort of surprising. But most of these will take iterators, like yeah, if you're trying to remove duplicates, it will need at least an iterator that can go forward. So the beginning position to remove duplicates from, and the position that's one beyond the end. So basically, you're going to give it begin and end. So a lot of these take iterators, but not necessarily every one of them. All right, so that's the rundown for these containers. Again, in our notes, particularly the second one here, where you really have to start using iterators, has examples of that. Here is a case with maps. So you get the first and the second with your iterator. And sets, likewise, they have insert instead of push front, push back, but you can use an iterator to access the elements. One thing I want to check, modern C++ has a keyword called auto that will figure out what the type of something is. So I wonder if we can actually just replace all this complex code with auto, and it will, when it compiles, it'll notice what type it has to be in order for it all to work out. Let's check if that works. Yep, so we're still good. So if you want to save some typing, particularly with iterators, because that gets pretty messy, you can start using auto. Auto works in a lot of other situations as well, when it's unambiguous what the type is supposed to be. In our third video on this topic, I'll explain the homework. The homework is going to be running benchmarks with the Google benchmark library to demonstrate that some of these operations, like inserting front and back and so forth, are more or less efficient for these different kinds of containers. And that will help you decide what to use when you confront situations in your future where you have to store data, but you got to figure out which container to use.